Kia ora koutou. In this video I'm going to do question 3 from tomorrow's scholarship calculus session. This one is one where we're given z is equal to a polar form complex number, so z is equal to this, and we have to show that it's a solution of this polynomial. Now we're told that we shouldn't attempt to find any other solutions of this polynomial. Usually I really like the hints that they give in scholarship exams. I think this one actually sets you off not seeing the easiest way to do this question. So I'm going to do this two ways, and I'm going to start by just deleting that. So suppose we're just asked, not even this, suppose we're just given this polynomial and we're asked to solve it. How would we do that? And if you do that, you've answered this question. Along the way, we'll end up showing that this thing is a solution. So, 4 terms, it's not a quadratic. It's clearly got some common factors. I'm going to start by doing my two-stage factorizing thing and just seeing if it gets me anywhere. So z to the power of 19 plus z to the power of 14 plus z to the power of 8 plus z to the power of 3 equals 0. Let's just put a little box around here and see what we can take out as a common factor. Well, we get z to the power of 14 times z to the power of 5 plus 1. Let's do the same thing now with the second little box. Oh, look at that. We've got z cubed into z to the power of 5 plus 1 equals 0. So this is just not using the hint at all, right? And we are going to end up, if we wanted to, we could easily, going this way, find all of the solutions of this polynomial. But that would be a bit boring. So now we've got z to the power of 14 plus z cubed times z to the power of 5 plus 1 equals 0. And we can clean this up and take out a common factor of z cubed. So z cubed times z to the power of 11 plus 1 times z to the power of 5 plus 1 is equal to 0. What solutions have we got? So z is equal to 0, or z to the power of 11 is equal to negative 1, or z to the power of 5 is equal to negative 1. If cis of 7 pi on 11 is one of these solutions, we've shown what is needed, or we've shown what's required. Now it's pretty obvious from looking which one's going to work. All I'm going to do now is I'm going to go ahead and I'm going to solve z to the power of 11 is equal to negative 1. So r cis theta to the power of 11 is equal to negative 1. And as you will have done many times in class, this is applying de Moivre's theorem to solve a complex root. So negative 1 is here on my argon diagram. We can write negative 1 as 1 cis of pi plus 2n pi, right? Remember that this number here is not uniquely cis pi. It could be cis pi, or it could be cis of 3 pi, or cis of negative pi, and so on. Cleaning this up gives me r to the power of 11 cis 11 theta is equal to cis of pi plus 2n pi, and that's by de Moivre's theorem. So 11 theta is equal to pi plus 2n pi. Now we're told not to find all the solutions, so we can straight away go to this. Theta is equal to pi over 11 plus 2n pi over 11. To generate cis of 7 pi over 11, all I have to do is to chuck the right value of n in. So when n is equal to, I've done something wrong in here, haven't I? I've missed a negative sign. Yep, there should be a negative there. Sorry guys, late at night, not enough coffee. Okay, that's more like it. Right, so it's negative pi. Well, it doesn't actually matter. It could be pi or it could be negative pi. Yeah, so actually it wasn't wrong. Negative pi is if I go around that way. Okay, I can feel people going down the YouTube at me. Man, she is having a slow day today. Sorry about that. Right, so negative pi plus 2n pi or pi plus 2n pi, it's both are fine. Right, now if we've got negative pi on 11 plus 2n pi, when we've got n equals 4, we get theta is equal to negative pi on 11 plus 8 pi on 11, which gives me 7 pi on 11. So we've found that our root is z is equal to 1 cis of 7 pi on 11 is a solution of the original thing, which I will go back up now and nicely label start. So there you go. But hopefully you can see that if I do it that way, I really can find all of the solutions of that polynomial, right? Because there will be, so there's one there of 0, there are 11 coming out here, and there are 5 more coming out here. This is really good basic practice at complex roots and de Moivre's theorem, but I'm not going to do it now. So that's the first way, right? And that's if you don't really look at the hint. Always look at the hint. The hints are nearly always going to make things easier for you. This is a kind of weird question like that. So the other way to do it is just to kind of guts it out and substitute this in here and hope that we get some nice trig patterns. So I'm going to do it that way now. I know some of you will be going, why is she doing it 2 ways? Well, because you never know when you're going to use this method in a different problem that you have to attack from this angle. So substituting in, I'm going to go ahead and slowly sub in this into here. And what do we get? Well, we get 7, cis of 7 pi on 11 to the power of 19, plus cis of 7 pi on 11 to the power of 14, right, so we'll call that P of cis of 7 pi on 11. And we're trying to show that it's equal to 0, which is 0 plus 0i. So the next obvious step is to apply de Moivre's theorem here. Good brain practice. What are 7/19s? 7/19s are 133 pi. 133. Next one, 7/14s. What does 7/14s give me? That gives me 98 pi on 11. And here we get cis of 56 pi on 11 plus cis of 21 pi on 11. Now this uses my spins idea again. What can I do to rewrite that so that it's something kind of sensible? Well, I can take out the multiples of 2 pi. So take out all the full revolutions. Good practice in, like, I don't know, year 5 skip counting. Let's skip count in 22s, right? We're looking for 22 pi on 11. So 22, 44, 66, 88. I'm not kidding. This is actually how I did it. 110, and then we get to 132. So we can rewrite this as just cis of pi on 11. Same thing here with the 98. We've got 22, 48, 44, 66, 88. So this is going to be cis of 10 pi on 11. This one, 56 pi on 11. Well, you might already be seeing that symmetry is going to be important in here. So I can either do 56 pi on 11 as being above this one, so as 12 pi on 11, right? 56 minus 44. Or I could do it as negative 10 pi on 11. I'm going to go really slowly with this and first of all do it as cis of 12 pi on 11. And that, guys, is because this is a teaching video. So if you're watching this and you're going, well, it's a bit slow, then I'm sorry, but I just want everyone to follow what I'm doing. In here, I'm trying to pull out multiples of 2 pi. So I haven't got one here. I've got 21 pi on 11. And now we're trying to clean this up and show that that all is equal to 0. But it's a show that question, so we can't skip steps too much. So what can I say now? Well, if you think about where these things are sitting, cis of pi on 11 is about here, right? And cis of 10 pi on 11 is over here. Now, cis of 12 pi on 11 is around here. So I'm going to rewrite 12 pi on 11 as cis of negative 10 pi on 11. I really, really like this question. I think it's really useful for your level 3 work because it gets you thinking about the different ways to write the argument of the complex number. So 21 pi on 11 is going to be negative pi on 11. And now you should be seeing some nice geometric properties. Remember that the cosine function is an even function, and the sine function is an odd function. We're going to write this out now and use some symmetry and some odd and even function stuff, and maybe a bit of graphing to finish it off. We're just about done. But you can see that, hopefully you can see this is much more work than the other way. So we've got cos of pi on 11. I'll do the real bits first. Plus cos of 10 pi on 11. Plus cos of negative 10 pi on 11. Plus cos of negative pi on 11. Plus I times sine of pi on 11 plus sine of 10 pi on 11 plus sine of negative 10 pi on 11 plus sine of negative pi on 11. So hopefully what you're noticing is that the first bit that cleans up is the imaginary part, because we know that sine of theta is equal to negative sine of theta, because we've got an odd function, right? The sine curve does not reflect in the y-axis, it rotates. Okay, so it's this picture up here is the one you want. That means that I can simplify this down to, I'll do two steps at once actually. So cos of theta is equal to cos of negative theta. Now that means that this and this are the same, and this and this are the same. So here we've got 2 cos of pi on 11 plus 2 cos of 10 pi on 11. Not that great yet, but when we get to the I part, the imaginary part, we've got sine of pi on 11 minus sine of pi on 11 plus this minus sine of 10 pi on 11, and that all equals 0. So what I'm left with is 2 cos of pi on 11 plus cos of 10 pi on 11. So two ways to think about this, both really good for the trig internal that's coming up. The first way is to think about the definition of cosine of theta as x over r and go back to your unit circle, right? So here's cos of pi on 11 out here, and here's cos of 10 pi on 11 out here. So you can see that cos of 10 pi on 11 is equal to negative cos of pi on 11. The other way to see that is using my graph. Let's just get the pen a bit skinnier before one of you complains that it's too wide. Right, so here's pi on 11, and this point here is pi. So 10 pi on 11 is sitting back here, and so you can see again that these are negatives of each other. In other words, cos of theta is equal to negative cos of pi minus theta. And that's enough to give me that this is equal to 2 times 0 as required. So we've shown that when we substitute that value in, we end up with 0, which means that it is a solution. So there you go, 2 ways to do that problem. 13-minute video really is probably faster to come to the session tomorrow morning. If you're watching this and it's the night before and you really need to sleep in, I am going to try and do all of these questions. So for just this week, that's fine with me. Thanks for watching.